Hello, everyone. Just give me 1 second. All right. So let's start. So today's topic is optics, as you probably have seen the assignment, and yeah. So, step one. Where's the chat? Here's the chat. There's a question about linear algebra. Are we doing linear algebra later in the course? I don't have a I don't have an answer. We have a matrix assignment, but I don't remember if we've removed it or we've left it. Okay, so I don't remember. But if you specifically want to do the matrix assignment, I'm happy to send it to you. Just email me and I'll send you over the matrix assignment if you're interested. But yeah. Okay, anyways. Today we're talking about optics, a fascinating topic. It's a specialty of Professor Lvovsky because he is an optics pro, and he works at an optics laboratory at Oxford, and it's amazing. It's because they have precision instruments which are very instruments with high precision. They are not allowed to vibrate. Yes, so the building was specifically designed to absorb all sorts of vibrations. So it's built deep underground. So if you ever go to Oxford, do try to visit this laboratory. It's quite cool. It goes very deep underground, like maybe 8 stories, 8 stories underground, and it has special absorption devices to absorb all the vibrations from the city. Just for the lasers that need to be very, very accurate. And I believe that's where they made a photograph of an atom, which seems impossible because the wavelength of an atom is larger than an atom. Nevertheless, they do have a photo of a single atom. Anyways, problem 1 in optics, and I really like this question. In a plane mirror, is the image always the same size as the object? What do you think? What do you think? Answer in the chat, please. In a plane mirror, is the image always the same size as the object? Plane means flat here. Okay, what makes you think that it is not? Can you explain the reasoning behind? Because if you tilt the mirror, it skews everything. Okay, can everybody take a mirror, or at least your phone, and look at yourself in the mirror? And if you tilt it, does it skew your image? Does it really? Your image disappears because you can't see yourself. Because you can't, it's not, you're not skewed. And yeah, please take a mirror or a phone so you can we're gonna do another experiment. Excuse everything. No, it doesn't. Yeah, the second question. If I stand really far back holding an apple, it'll appear small, but it's the same size in my hand. But you appear like, I mean, if you stand far away from anything, it looks small, doesn't it? If you stand far away from a car, it looks tiny. It's like if I can't see myself. Where's my video? Ah, that's how you do it. If I, so there's something behind me. I don't know. If I hold it like this, certainly my cupboard can't fit. My cupboard certainly doesn't fit between my fingers. And so yeah, if you stand far away from anything, anything looks small. Is the reflection the same size regardless of distance? Well, I don't know what you mean by reflection. A reflection is not a thing. Are you referring to the image? The image that you see in a mirror. So, image in a mirror. Image in a mirror. So clearly you can see that in this mirror, the image is exactly the same size as the object, as the person being reflected, right? So that's quite, that is true for mirrors. So for example, this one also. So copy image. The mirror image in a mirror is the same size. The image in a plane mirror. Image in a plane mirror. Mirror. First, it is the same size as the object. Two, it is the same distance from the mirror as the object. As you can see, the distance from the object to the mirror is the same as the distance from the image to the mirror. That's quite cool, if you ask me. Distance. We call this u, the distance from the object to the mirror, u, and the distance from the image to the mirror, we call it v usually. They are the same, so u equals v. The height, ho, object, and hi, h image, is the same. H object in distance as the mirror from the object, and it is laterally inverted. 3, it is virtual, and 4, it is laterally inverted. means left is right and right is left. Laterally inverted. It is virtual in the does everyone know what virtual means? What and why an image is a virtual image? But what do you mean by not a physical thing? Oh, your eyes is deceiving you, but your eyes doesn't interact with the world. That's not the definition. The definition is light rays. Light rays don't actually. So if you place a screen, there will be no image on the screen. As opposed to a lens image with a convex lens. So for example, I like this photo. If you take a lens and what you see here is this is a candle. This is the object. Candle. And this is the image of that candle. So you can do this experiment at home as well. If you take a lens and a candle, you can do that. And it's quite fascinating. You can do it with, you don't have to use a candle, you can use your phone. So if you take your phone and a magnifying glass, you can project your phone onto the wall in a dark room. So I've done this. It's quite cool. You need to play around with the distances a little bit, but do try this at home. Take a magnifying glass, take your phone, and get an image of your phone on the screen. That's how projectors work, right? That's how it just projectors are a little bit brighter. This is a real image because it can be shown on a screen, because it can be shown on a screen. As opposed to, for example, as opposed to this image. The woman seems to be behind the wall. And if you place a screen behind the wall, you won't see anything on the screen. Does that make sense? If you place a screen, like this is like, you don't even know what's in here. It could be a forest. It could be outside. If you place a screen here, there won't be nothing shown on the screen. Okay. Now, but then a lot of people, and me, including me, have a problem with the first point. Image in the plane mirror is the same size as the object, but is it? Is it? Why it is confusing, I will demonstrate. So this is my mirror. I have to switch off the blurring because otherwise it's just unblur. Yeah, okay. So do you see a house in my phone? Now, doesn't that contradict the first point? Doesn't that contradict that the image has to be the same size as the actual object? Well, it's not. I know the people living in that house and they're normal sized people. They do drive a ridiculous car, but that's not the point. What is further away? Archie, yes. The house looks the same size as it does to you looking through the window. Absolutely. It looks exactly the same size as if you were looking through the window. Carry from the mirror to the virtual image. Very good. The distance is the same distance. You need to look at point 2. The distance from the mirror, which is my phone, to the virtual image of the house is the same as the distance from the house to my mirror. So if you do a diagram, it becomes very clear. So this is the house. The house is very big. It's normal size house. This is my small mirror. This is my small mirror. But then the image of the house is the same distance. So the image is right here. The image of house. This is the house. And I'm standing here. I'm standing here with a small mirror and I'm viewing the image through my phone. It's as if you're looking through, like if you make this and you can look at your house the same way, is just in reverse. I'm looking at the house through a mirror. So the image is exactly the same size as the house. It's just the image is so far away that when I look at it through my small mirror, I can actually see the whole house. Julian, no, it doesn't have anything to do with 1 over f plus 1 over u. That's for convex mirrors. Sorry, that's for convex lenses and concave mirrors, if I'm not mistaken. Yeah. Yeah, it's just with the for concave lenses, it's going to be a minus, but that's not important. Does that make sense? That it is the same size. It is the same size. It's just because it's far away, that's why it looks small. All right, any questions here? So just to recap, this is my mirror. This is the house. The house is way over there. The image of the house is the same distance, but in that direction. So it's about what, like 70 meters in that direction. And there's obviously nothing there. If I place a screen there, I won't see anything on the screen. All right, no questions? Good. What is the minimum size of a mirror so you can see yourself standing up? So clearly you can see that, well, we don't know what the lady sees. The lady might see herself fully standing, probably not, but Anyways, what is how big does the mirror have to be in order for you to see yourself standing upright? So part two of the problem. So here's you. Yes, Jed, that is correct. But how do you know that? You and your image. Yes, absolutely. It's your image. Your image. Well done. Your image. So, no matter how big the mirror is, it doesn't matter. Even if the mirror is like this, is very small, your image would still be here. Like moving the mirror downwards doesn't change the position of the image. It's just if you place the mirror over here, you won't really see yourself because what you see is determined by the position of your eyes. This is what you're going to see. You're going to see stuff above your head. So that's pointless. That's why you don't place a mirror on the top. So you need a mirror somewhere here. And in order to see yourself fully, you draw lines from your eyes to the bottom of your image, and then to the top. So this way you can see yourself. And the mirror has to be of this size. So if this is your height, if this is your height, h, this distance is L, and this distance is also L, because we already established that you are the same distance from your image. Then these are similar triangles, right? And you can safely say that this is h over 2. Does that make sense? Do you understand? Okay, how well do you understand this on a scale of 0 to 10? Mirror has to be half your height. I think the most important thing here is that your image would still be here, exactly in this position, regardless where you put the mirror. So if you put the mirror here, your image won't move. You won't see it. It's still there, but you don't see it. That's an important concept. If you have a mirror, there is an image. You don't necessarily see it. Okay, good. Hope that a nice exercise to start with. Some thoughtful stuff. So imagine a prism. So this is I like this simulation. So fed bending light. Bending light. It's a very nice simulation. Okay, and if you take a prism, so here's a prism, and you shine some light through a prism, it bends twice. And if you draw the normals, you can then measure the angles of incidence and angles of refraction. Okay, so at some point, you can have a situation where light doesn't escape. So we have refraction, refraction, and now you have refraction, reflection, refraction. We'll talk about this in a bit, but that's the idea. So here we say that this angle is θ1. Yes, that's total. This is θ2. This is θ3. This is θ4. So this is the angle of incidence. This is refraction. This is incidence, and this is refraction again. And for the first boundary, so assume that the glass has a refractive index n1 and air has a refractive index n0. Then we write sine θ1 over sine θ2. Now, here's a trick I like to use because I'm not very good at memorizing formulae, honestly. Sine θ1 over sine θ2. I don't remember. Is it n1 over n0 or is it n0 over n1? What do? I look at the angles and I see that θ1 is greater than θ2. θ1 is greater than θ2. So sine θ1 over θ2 is going to be greater than 1. So this fraction is going to be bigger than 1. So I need the bigger refractive index on top, and glass certainly has a bigger refractive index than n0. So it's going to be n1 over n0 rather than n0 over n1. So this is a trick I use when I do Snell's law. Oh, yes. Sorry. This is confusing because n1 is θ2. Okay, let's stick with n1 and n2. N2 and n1. So it's the bigger one divided by the smaller one. So n2 divided by n1. Sorry, that must have been confusing. For the second boundary, I can write that sine θ3 divided by sine θ4. Now, this θ3 is a smaller angle, θ4 is the bigger angle. So I need the smaller divided by the bigger one. So it's n1 divided by n2. Okay, and that's that. And then I can use these formulae to express, I don't know, θ4, for example. Now, let's there's another thing here that we need to work out. Well, okay, let's go here. So for a 60-degree prism with a refractive index 1.5, calculate the minimum incidence angle that does not produce total internal reflection within the prism. Or basically find the angle at which we have total internal reflection. So total internal reflection would. So what happens for the total internal reflection? Total internal reflection happens when the angle theta 4, which is this angle, theta 4, this angle, becomes 90 degrees. So right about here. Okay. So total internal reflection, TIR, occurs when theta 4 is 90 degrees. Okay, let's use that. So the refractive index of glass is 1.5, and this angle is 60 degrees. It's 60-degree prism. So theta 4 is 90 degrees. So sine theta 3 divided by sine theta 4, as we have already established, it's smaller divided by bigger, so it's going to be 1 divided by 1.5. And theta 4 is 90 degrees, so that's equal to sine theta 3 divided by sine 90, which is 1. So sine theta 3 is 1 divided by 1.5, which is 2/3. I don't really need to calculate theta 3 at this moment because I know the sine of the angle. Now I'm looking for theta 1. So effectively it says find theta 1 if theta 4 is 90 degrees. That's what I need. So sine, okay, now I need to find a link between theta 2 and theta 3. What can I do here? Well, this is theta 3, and this is 90 degrees, which means that this angle is 90 minus theta 3. This angle is theta 2, and this is 90 degrees, which means that this angle is 90 minus theta 2. And using the triangle, because we can use this triangle, we can say that alpha plus 90 minus theta 2 plus 90 minus theta 3 has to be 180 degrees. And alpha is 60 degrees. So 60 degrees plus 90 minus theta 2 plus 90 minus theta 3 equals 180. And look, 90, 90, 180 cancel. And we have theta 2 plus theta 3 is 60 degrees. Well, okay, it looks like I will need theta 3 in order to find theta 2. Okay, that's fine. I can do that. Theta 3 is arc sine 2/3, which is arc sine 2 on 3, 41.8 degrees, roughly. And then that means that theta 2 is 60 minus 41.8, which makes it theta 2 is 60 18.2 degrees. And then we have sine theta 1 over sine theta 2 is going to be, so the refractive index of air is 1. Air is 1, and this is 1.5. So theta 1 is greater than theta 2. That's why I can say, oh, that's going to be 1.5 divided by 1. Really, it's really helpful rather than trying to remember and not mess up. Just use common sense. Sine theta 1 is equal to 1.5 multiplied by sine 18.2 degrees, which is uh, the answer 1.5 times sine, which is 0.4682, and that theta 1 is arc sine of that, which is 27.9 degrees. Let's see if that actually makes sense. So it's about 27.9 degrees. That's my answer. That's the angle at which the prism will go to TIR, total internal reflection. This is a 60-degree prism. This is exactly what we have here. This is an equilateral prism. And they say that the angle of incidence is 27 when TIR occurs. Okay, so let's see. Oh, we forgot the refractive index of glass. Oh, that's, yeah, it is glass. Okay, that's fine. It is about 1.5. Glass. Okay. Okay, let's measure. Angle of incidence. Does look like about 27, 28 degrees. Can we? Oh, we can't get the angles, but yeah, it does. So it does correspond to reality. So as you can see, indeed. So the angle of incidence is indeed about 27.9 degrees, as you can see here. Nice. Then the next thing I wanted to talk is about optical fibers. And optical. Have you done optics in school, by the way? Have you done the topic? Yes or no? Okay. All right, not yet. All right. Can somebody tell me why the cladding in the core have to be very similar in refractive index of the cladding has to be very close to the refractive index of the core. So the refractive index of the core has to be greater than the refractive index of the cladding, but it's a very small difference. For example, here you get 1.55 and 1.49. Sometimes you could have 1.51 and 1.52, for example. To maximize the critical angle. Yes, that is true. Do you know why we want to maximize the critical angle? To reduce the distance the rays travel. Why is that important? Okay, so I'll go in order. The rays don't escape the cladding, but that that actually means that they will, doesn't it? They will. The rays. Oh, the cladding. They will escape the cladding. No, they're not meant to. Then the rays are not meant to go into the cladding. So you have the core. So you have the core. So the core. Let's say the core has a refractive index of 1.5. So the critical angle would be critical angle would be for the core is going to be arc sine of 1 over 1.5, which is about 42 degrees. 42 degrees. So if an angle, if a light ray falls at 42 degrees or more, it will reflect. Okay. But if you have a core and a cladding, cladding is wrapped around the core. So it's two layers. So you have the core and you have the cladding, top and bottom cladding. Let's see if there's a decent picture of optical fibers. Optical fibers. So here it is. The cladding is outside the core. And this, you see the light goes in and it bounces back and forth through the optical fiber. And yeah. But if you have the core in the cladding, so let's say the core is 1.51 and the cladding is 1.52 and the cladding is 1.51. So here the refractive index is 42 degrees. That is arc sine of n of 1.5 of 1 over 1.5 because air is 1. Air is 1. This is 1.5, which is approximately 42 degrees. Here, the critical angle is arc sine of 1.51 over 1.52, which is approximately, I'm guessing 88 degrees. Arc sine of 1.51 divided by 1.52. 83.4 degrees. So by introducing the cladding, we're increasing the critical angle. That means a light ray falling at 42 degrees will now escape. Anything below 83 degrees will escape. So only some of the light, only the light that goes through at a very so this will escape. Only the light that goes very close to the middle will pass through. Everything else will escape. They won't lose intensity. Once again, that doesn't do anything because you're losing light. Some of the light will escape at the beginning, and only the light that falls at a very shallow angle will pass through to the end. So there's less delay between parts of the signal. That's very good to prevent signal degradation. Dispersion, that is, yes, Karim, you're correct. That is called multi-path dispersion. To avoid dispersion, repeaters the less signal decay, the less repeaters you need to install. I'm not sure what you mean by decay. By decay, you mean the signal will degrade, or do you mean the intensity? You will lose intensity. Okay. So yeah, what happens is this is called multi-path dispersion. Multi-path dispersion. How it works. So if you have an optical fiber, and an optical fiber is used to transmit signals. Now, without the cladding, you are allowed to travel like this, for example, bouncing back and forth. Or you can bounce like this. And the same signal, well, one signal. So for example, 1 bit. If you have the signal comes in, a single bit, so a 1, will pass on, but because it travels in 2 different paths, by the time it arrives, it will split into 2 distinct signals, because one part of the signal takes longer than the other part. Well, actually, it won't look like 2 signals. No, I'm lying, because it will look. I will show how it looks like. The it's the red path takes longer time. So the same signal will eventually effectively spread out. So you start with the signal, and when you transmit, it will become something like this. So this 1 becomes this, it becomes dispersed. And if you have a sequence of 1s and 0s, so for example, if you want to send a signal, like 1 1 0 1 1 0 1, by the time it reaches the other end, it will look more like what's that? 0 1 0 1. The computer might, well, yeah, basically these 1s and 0s, they will scoosh together, and you'll hear noise there, and the computer will make mistakes. Where you're expecting 0s, it will bring 1s, and vice versa. Hope that makes sense. That's why when you introduce the cladding, you're only allowed only the light traveling at very, very shallow angles will get through to the other end. Okay, so we have the core and the cladding. And an optical fiber has a core with a refractive index of 1.55, and a cladding with a refractive index 1.49. Calculate the angle of acceptance. Angle of acceptance is the maximum incidence angle that can produce a total internal reflection. So basically, the optical fiber accepts that ray for traveling, or it doesn't. If yeah, so that's what we need to work out. So we have the system. So this is theta 1. This is theta 2. This is theta 3. And this is theta 4. So once again, we're looking for theta 1 if theta 4 is 90 degrees. Okay, so we want to know the maximum angle at which we can actually pass maximum. Yeah, maximum. The maximum angle at which we can send the signal through the optical fiber. All right, so but the calculation is the same. Okay, so very quickly we can do theta sine theta 4 divided by sine theta 3 is and we know that theta 2 plus theta 3 has to be 90 degrees because that's alpha. And sine theta 4 and sine theta 3. So that's 4 is bigger. 4 is 90 degrees. So that's 1.55 divided by 1.49. So sine theta 3 is 1.49 over 1.55. So theta 3 is arc sine of 1.49 over 1.55. Okay, arc sine 1.49 over 1.55 is 74 degrees. 74 degrees. That means theta 2 has to be 16 degrees. And theta, we can work out theta 1. Theta 1 is going to be arc sine of 1.55 multiplied by sine 16 degrees. So arc sine of 1.55 times sine 16, which is 25.3 degrees. So that's the maximum angle at which you can send. So what does that mean? Well, that means that if you have the core and the cladding, and you're sending a signal at, for example, 32 degrees, it will okay, sorry, you're sending a signal at 32 degrees, which is greater than that angle. It will travel this, and that it will escape into the cladding. It won't reach the other end. But if you send a signal at a shallower angle, for example, this is to 22 degrees. It will refract and then bounce off, bounce off, bounce off, etc. So that's what is meant by the acceptance angle of a optical fiber. Now this is another problem. I'd like to go through problem 6 first, using the Fermat's principle. So the problem is as follows. So imagine that you live on a lake, on the beach, and imagine that this is your house. Okay. And one morning you walk out of your house and you see somebody in distress. So somebody here crying for help. Help. Okay. It may or may not be the person of your dreams, maybe your future wife or husband. Anyways, you want to save them because you're a good human being. Question is, how do you get there in the shortest time possible? And assume that the shoreline is like this. Well, what are the options? Well, you can run to the water and then swim. Or you can go in a straight line, or you can run to this point and then swim from here. You could go in a straight line, which is the shortest path. Okay, it doesn't look like the shortest path, but you got the point. Or something in between. Basically, you need to choose the point where you enter the water. This is the point where you enter the water. Let's say we don't know where you enter the water, but let's say that this is the point that you enter the water. So you run to this point, and then you run this way. Okay. So let's do some geometry. Maybe just make another sketch. Okay. So this is the borderline, and this is you. This is your house, and this is the person in distress. So you want to run somewhere here, and then you want to go here. Okay. Let's say that this distance is L, and this distance is, let's call it L1, and this is L2. And this is the point where you enter the water. And let's say that this is X1 and X2, the horizontal distance. Okay. And then here, This would be quite useful. Let's call this angle theta 1, and we'll call this angle theta 2. Okay. I hope that makes sense. All right, so you walk from your house. Let's call it A, B, C. Let's call it D and E. I think that should suffice. All right. Now you want to run from A to B. The time from A to B is the distance from A to B, this is AB, divided by your speed. And the speed of your run. Oh, let's call it V1 for simplicity, V1. And the time from B to C is BC divided by the speed at which you swim. So V1, it's the running speed, and V2 is your swimming speed. And if you're like me, you probably run faster than you swim. Okay. So V1 is greater than V2. Okay. It's probably one of my favorite problems in physics. You probably see what I'm getting at. Does everyone understand the problem that we're trying to solve? You're trying to minimize the time to reach point C. So you're at point A, you need to go to point C. Any questions of the setup of the problem? The time to run from A to B and the time to run to B. So AB, now AB is going to be, well, using Pythagoras, this is L1. This is L1 squared plus x1 squared, square root, divided by V1. And BC, by, again, Pythagoras, is the square root of L2 plus x2. Probably, but that's what I'm trying to prove. I think you're right, Archie, but that's what I'm trying to prove. Squared. All right. Now, what is theta 2? Well, oh no, sorry. No, don't, let's not do this yet. We're going to express, all right. What I'm going to do is I'm going to denote this value as, let's call it, not D, but L. Let's call it L. And this we'll just call X. We'll call X, and this, therefore, L minus X. L minus X. Now, AB. So what is AB? Well, if you look at the triangle, so this is theta 1, this is theta 1. Sine theta 1 is going to be X divided by AB. And sine theta 2, similarly, is going to be L minus X divided by BC. So from here, I can write that AB is X divided by sine theta 1. And here I can write BC is L minus X over sine theta 2. So TAB is going to be X divided by V1 sine theta 1. And this is going to be L minus X over sine theta 2, but V2 sine theta 2. And the total time total is AB, so it's X divided by V1 sine theta 1. Sorry, that's nonsense. No, that's not what I want to do. Sorry. I'm getting ahead of myself. You know what? I will express. I will not do the last step. This is too much. Okay, AB. Okay. Oh no. So X over, okay, V1. All I need to do is just undo. Okay, so let's see. Let's see what we can do next. So the total time, is X over V1 sine theta 1 plus L minus X over V2 sine theta 2. Okay. Now theta sine theta 1 is X over AB, but AB is not fixed. AB is yeah, I'm trying. Yes, that's what I need to do. The problem is, so why I can't differentiate, because theta 1 depends on X. Theta 1 depends on X. That's why I can't do anything. All right, no, I have to revert to L1. Sorry, no, that's I was seeing that as a problem. It's not. No, sorry. Once again, the initial approach was correct. So AB is square root of X squared plus L1 squared divided by V1. And BC is going to be square root of L minus X squared plus L2 squared. Okay, this is divided by V2. And here, from here, the total time is square root of X squared plus L1 squared divided by V1 plus square root of L minus X squared plus L2 squared over V2. So now in order to find the minimum time, I need to differentiate t with respect to x. Okay, find x such that t is minimum. Find x such that t is minimum. All right, so dt over dx. So I differentiate that. So it's going to be 2x multiplied by minus half. So a half multiplied by square root by x squared plus L1 squared to the power minus a half and multiplied by 1 over v. 1, I believe so. Have I messed anything up? No, I don't think so. Okay. Plus differentiating that. So that's going to be, oh wow, it's going to be 2 L minus x multiplied by minus 1. Yeah, multiplied by minus 1. Multiplied by 1 on 2 square root of L minus x squared plus L2 squared multiplied by 1 over v2. And this has to equal to 0. Okay, so let's try to make sense of that. So this is x over v1 square root of x squared plus L1 squared plus x minus L v2 square root of L minus x squared plus L2 squared equals 0. So x multiplied by v2 square root of L minus x squared plus L2 squared. Oh, I see. I think, yes. Now we do a trick. Remember, what is AB? What is sine theta? Yes, that's how it works. Sine theta 1 is x divided by AB, and AB is square root of x squared plus L1 squared. Aha, so that is sine theta 1. And surprise, surprise, sine theta 2 is a very similar expression. This expression is minus sine theta 2. So sine theta 1 over v1 minus sine theta 2 over v2 is equal to 0. In other words, sine theta 1 over v1 equals sine theta 2 over v2. And that means that v1 over, sorry, sine theta 1 over sine theta 2 is equal to v1 over v2. Effectively, this is the Snell's law. If you want to reach point C as fast as you can, you need to follow the Snell's law. Quite cool. And you will have a problem on that. There's a problem, the last problem of the assignment is pretty much the same as this one. Okay. So I've just solved one of the problems from the assignment, almost. Okay. And I don't know. I find it quite fascinating, the link between light and minimizing travel, as if light has some sort of intelligence that it knows how to get there in the shortest possible time. This is the Fermat's principle. Least time, Fermat's least time principle. Least time principle. I think I'll stop here for today. Any questions? Questions? I'll skip this. I'll skip problem 5. Maybe do it next time. Right. Okay. If there's no questions, then I'll see you all next week. I'll do some more maths. All right. See you, everyone. You can watch my other webinars on this topic. They are available. You're welcome. See you. Oh yeah, Rakesh, go ahead. Problem 14 in maths. Let's have a look. You need to change your base formula for this one. So for example, if you have log, I don't know, x7, you could write it as log 7 divided by log 7x. And now you have, well, it's 1 over log 7x. Yeah, so change of base formula. So you want to get rid of, you don't want x in the you don't want x in the base of the logarithms. That's the first thing I see. I see x as a base, and it's like no x bases. Does that make sense? Okay. All right. See you then.